Looking quickly at the crunch machine problem, we're going to regard the system here as the 30 kilograms of my upper body mass plus the machine. Now that might seem a little weird. It actually does seem a little weird because, of course, we're splitting me into my upper body that's descending with the crunch motion and the abdominal muscles that are causing that. But that's a valid way to regard the system. The part of my body that loses potential energy and the machine. That's the system. Even though my abs are actually part of that 30 kilograms, the effective part, they don't move as far as most of my upper body does, but they do lower some, so they contribute their potential energy to the process, some of the potential energy. Okay, so anyhow, on the descent in the crunch machine, the change in potential energy, if we assume that I have, and I apologize, this isn't very easy to read, but the calculation is very straightforward. We have the 30 kilogram mass descending 0.3 meters, multiply the 30 kilograms by 10 meters per second squared, which is the approximation of the 9.8 meters per second squared of gravitational acceleration, to get the weight of the descending part of my body by the 0.3 of a meter to get a 90 joule change. 90 joules of work are done by gravity in the descent. And that gives us a change equal and opposite to the work done by gravity, negative 90 joules. The work done by me is 300 joules. That's the 500 newtons of force and the 0.6 of a meter. Now I'll mention that the 0.3 of a meter, 0.6 of a meter, and probably 30 kilograms are all, I think, somewhat overestimated, but that's okay. Okay, so to do the energy conservation then, the work done by the net force on the system is the work done by me on the system plus the work done by gravity on the system. And that, of course, equals the change in kinetic energy of the system. Since I start the crunch motion stationary and end the crunch motion stationary, the change in kinetic energy for the descent is 0. Okay, so the work done by gravity on the system is what? The work done by gravity on me, which is the work done on that 30 kilograms of me that descends, and the work done by gravity on the stack. Now that's totally illegible, but that's what that says, and we know that. The work done by gravity on me is 90 joules, equal and opposite to the change in potential energy. And the work done by gravity on the stack, well, we don't know that, but we're going to get that in just a minute, is equal and opposite to the change in the potential energy of the stack. So the work done on the system by the net force is the 300 joules of work I do, the 90 joules of work gravity does on my descending mass, that portion of my mass, minus the change in potential energy of the stack, and that's equal to the change in kinetic energy, which, as we see, is 0. It follows then that the change in the potential energy of the stack has to be 390 newtons. 390 newtons here minus potential energy equals 0. Clearly, the potential energy change of the stack is 390 newtons. Now, if the stack rises 0.8 of a meter, then what's the weight of the stack? Well, the weight is going to be the amount of work done on the stack divided by the 0.8 meters. And we're not going to worry about plus and minus signs. It's pretty clear that we're talking about 390 joules done by gravity as something moves 0.8 meters. And that comes out somewhat less than 490 joules, but pretty close. 487.5, I'll bet you. You can work that out. Okay, now friction is there. We could measure the force that it takes to make the machine descend, and then the force that is exerted by the machine as we slowly raise it. So force on a slow descent, force on a slow rise. The difference in those two forces is going to be due to friction within the machine. We could work all that in. The other thing is that my abdominal muscles are not doing the whole 300 joules. Well, my abdominal muscles are not exerting the whole 500 newtons. Okay. My abdominal muscles are not doing all the work to raise that stack. The potential energy loss is doing what? About 9,390ths, or about 3/13 of the work to raise that stack. So I'm going to have to lower my estimate of what my abdominal muscles do. The motivation for this whole thing is simply I had an injury that took a while to heal and had to reduce the weight that I was lifting with that stack, and reduced it to about 60%. And I know that when you reduce from a weight that's near your capacity to 60% of that weight, it doesn't feel like you're doing much. It felt like even less than that. So I got to thinking, well, why does it feel like so little? Well, I'm aware that my upper body's kind of flopping over the machine and helping to lower it. So I just, made up these numbers to somewhat explain some of that perception. Naturally, I could do some measurements on the machine. I might even do that. I might take one of our spring balances down there and do some measurements, because it's kind of an interesting system. But we might or might not do that. Right there's the general idea. The general overall concept of where energy goes in the use of this machine. Now, we haven't talked about what happens when we come back up, but you can think about that.